Hello, good day. Today's topic is grid search and random search from the machine learning. So, what is grid search? Grid search is a fundamental hyperparameter techniques in machine learning used to find the optimal settings for a model by exhaustively evaluating a specified subset of hyperparameter space. Unlike model parameters like weights, which are learned during training, hyperparameters like learning rate or tree depth or shed manually before training can significantly influence model accuracy. Code mechanism grid search works by creating a grid of all possible combinations of randomly defined hyperparameter values. Sequential evaluation, the algorithm trains and evaluates a separate model for every single combination in the grid. Metric-driven selection, it uses a performance metrics, example accuracy, FN score, or RMSE, to rank these combinations. Cross-validation integration, most implementations such as scikit-learn, gridsearch CV, use K-fold cross-validation to ensure that the chosen hyperparameters generalize well to unseen data rather than just fitting the training set. Comparison with other techniques, feature grid search, random search, Bayesian optimization, such strategy exhaustive tries every predefined combination, randomly samples combinations from a distribution, a smarter search based on past iteration in results. Speed slowest can take a long time for large grids. The faster budget is independent of grid search, grid size, efficient finds optimal values in fewer iterations. Best use case is small, well-defined, and large or continuous search spaces, complex models with expensive training times. So, what are the advantages of the grid search? Like advantages are thoroughness guarantees finding the best combination within the provided grid. Simplicity, highly intuitive and easy to implement using standard libraries. Parallelism evaluations are independent, making it embracingly parallel across multiple CPUs or GPUs. Limitations, computational cost suffers from the curse of dimensionality. As you add more hyperparameters, the number of combinations grows exponentially. Inefficiency may spend a significant time evaluating clearly suboptimal combinations. Implementation in Python, the standard tool for this technique is the gridsearch CV class from the scikit-learn library. A typical workflow involves defining a model, choosing an estimator like support vector machines, SVM, or random forest. So creating a param grid, a dictionary mapping hyperparameters names to lists of values to test, fitting the search running fit of on the training data, which executes the exhaustive search and cross-validation, extracting results, accessing best params and best score to retrieve the winning configuration. Hyperparameter tuning is the process of selecting the optimal values for a machine learning model's hyperparameters. These are typically set before the actual training process begins and control aspects of the learning process itself. Effective tuning helps the model learn better patterns, avoid overfitting or underfitting, and achieve higher accuracy on unseen data. Techniques for hyperparameter tuning. Models can have many hyperparameters, and finding the best combination of parameters can be treated as a search problem. The two best strategies for hyperparameter tuning are the gridsearch CV is a brute force technique for hyperparameter tuning. It trains the model using all possible combinations of specified hyperparameters values to find the best performing setup. It is slow and uses a lot of computer power, which makes it hard to use with big data sets or many settings. It works using low steps. Create a grid of potential values for each hyperparameter. Train the model for every combination in the grid. Evaluate each model using cross-validation. Select the combination that gives the highest score. For example, if we want to tune two hyperparameters C and penalty for a logistic regression classifier model with the following sets of values. C is equal to 0.1, and so on. And the penalty will be like 0.01, 0.1, 0.5, 1.0. So these are the values which we will get in the research. And research technical construct multiple versions of the model with all possible combinations of C and alpha, resulting in a total of 5 plus 4, that is 20 different models. The best performing combination is then chosen. Example tuning logistic regression with grid search CV. The following code illustrates how to use grid search CV. In this below code, we generate sample data using make classifications, and also we define a range of C values. Is a logarithmic scale. Grid search CV tries to all combinations from a parameter and uses fivefold cross validation, which returns the best hyperparameter C and it corresponds to validation score. So these are the thing. So we will get the output of this particular code as tuned logistic regression parameter C as so and so, and best score is 0.0853. This represents the highest accuracy achieved by the model using the hyperparameter combination C is equal to 0.0061, and the best score of 0.853 means the model achieved 85.3% accuracy or the validation data during the grid search process. So next is randomized search CV. So as the name suggests, randomized search CV picks random combinations of hyperparameters from the given ranges instead of checking every single combination like grid search CV. In each iteration, it tries a new random combination of hyperparameter values. It records the model's performance for each combination. After several attempts, it selects the best performing set. So, example tuning decision tree with randomized search CV. The following code illustrates how to use randomized search CV. In this example, we define a range of values for each hyperparameter. Example max underscore depth, min underscore samples, underscore leaf, etc. Random combinations are picked and evaluated using fivefold cross validation. The best combination underscore are printed. So this is sample code, like I said in here. So we define the values hyperparameter, example max depth and max min samples. And next is you're creating a nation tree, and using the randomized search CV, we pass on the tree params and test, and CV is equal to 5. So then you're finding the tuned nation tree parameters, and also the best score is output will be like this: tune decision, tree parameters, criteria, and entropy, max and score depth, and max features, equal to 6, samples 6, and the best score is 0.8. That is the score of 0.842 beats the model performed with an accuracy of 84.2% on the validation set with the following time parameters. Sorry, on the validation set with the following parameters. The Bayesian optimization is something like the grid search and random search can be inefficient uh, because they blindly try many parameters combinations, even if some are clearly not useful. Bayesian optimization takes a smarter approach. It treats hyperparameters tuning like a mathematical optimization problem and learns from past results to decide what to try next. Build a probabilistic model, surrogate function that predicts performance based on hyperparameters. Update this model after each evaluation. Use the model to choose the next best set to try. Repeat until the optimal combination is found. The surrogate function models P of score of y to hyperparameters of x into P of score of y to hyperparameter of x. Here, the surrogate function models are the relationship between the hyperparameters x and the score y. By updating this model iteratively with each new evaluation based on optimization makes more informed applications. Common circuit model used in Bayesian optimization include Gaussian and process random forest regression, tree structured Gaussian estimator (TPE). Advantages of hyperparameter tuning or like find the optimal combination of hyperparameters can significantly boost model accuracy and robustness. Tuning helps prevent both overfitting and underfitting, resulting in a well-balanced model. By selecting hyperparameters that perform well on validation data, the model can generalize better to unseen data. It also helps in using computational resources like time and memory more efficiently by avoiding unnecessary trials. Proper tuning can make the model simpler and easier to understand and interpret. Challenges large hyperparameter spaces increase the number of combinations to export, making the process computationally expensive and time consuming. And also, especially for complex models and using real knowledge helps narrow the search space, improving both efficiency and effectiveness of hyperparameter training. Dynamically adjust hyperparameters during training, such as learning rate, sensitivity, or early stop, in can improve model performance. Randomized search is a hyperparameter optimization techniques that sample yields a combination of hyperparameter values from the defined search space rather than exhaustively testing every possible configuration. This approach is widely used to improve model performance by balancing computational costs, particularly in high-dimensional or continuous parameter space. Key concepts of randomized search: sampling. So, in the key concepts of randomized search sampling strategy, unlike grid search, which tests every point on a fixed grid, randomized search draws a fixed number of samples and entires of statistical distribution, example, long, uniform, or normal, or discrete. Less computational efficiency, you can specify a budget number of iterations increment of the number of parameters, making it significantly faster for complex models. Exploration potential, it can discover it can discover it can discover optimal values that might fall between the fixed intervals of a grid search, especially for continuous parameters. Cross-validation, it is typically combined with cross-validation in some database search CD and expected none to ensure that selected parameters reflect well to unseen data. So the advantages and disadvantages of random search and grid search are like saving features of search space. In dynamic search, better for higher dimension or continuous space. In grid search, best for small, discrete, and well-defined space. And the next is resource use features like in database search, high users control time by setting entire. In grid search can be extremely costly as parameters increase. So guaranteed features are like no guarantee of finding the global optimum random search, and in research guarantees finding the best set within the provided grid. Parallelization, trivial each iteration is independent in random search, and trivial evaluation in grid search. Advanced randomized techniques beyond simple random sampling. Several guided or advanced randomized techniques exist. Successive halving and iteration selection process where my uh, where my candidates start with small results. So again, advanced randomized techniques. We are simply random sampling from both guided or advanced randomized techniques exist. Successive halving, that is the primary gradient selection process where many candidates start with multiple samples. Example, few training samples and only the best survey if the next rounds with more resources. Halving random search CV implements this in scikit-learn simulated annealing. See a probabilistic method that allows accepting worse solutions initially to escape local minima, gradually narrowing focus as the temperature cools. Randomized hill climbing or NC starts with a random point and then iteratively explores its local neighborhood for improvement. Neural architecture search NAS random search is frequently used as a competitive baseline for discovering optimal neural network structures. Implementation workflow define parameters, space create a dictionary of hyperparameters and their corresponding distributions, example uniform gradient. Initialize search object use a tool like randomized search CV, specifying the estimated param underscore distribution and entire and CV number of folds. Fit and select run the fit method on the training set. The best will automatically select the best params based on cross validation scores. Evaluate test the resulting best. So evaluating the test the resulting best model on the separate test set to verify its performance on new data. Comparing randomized search and grid search for hyperparameter estimation in scikit-learn, hyperparameters are the parameters that determine the behavior and performance of a machine learning model. These parameters are not learned during the training but are instead set prior to the training. The process of finding the optimal values for these hyperparameters is known as the hyperparameter optimization, and it is an important step in the development of any machine learning models. And there are many different methods of performing hyperparameter optimization, but two of the most commonly used methods are grid search and randomized search. In this blog post, we will be comparing the two methods and provide examples of the how they will use in this case. Python. Grid search hyperparameter estimation. Grid search is a method for hyperparameter optimization that involves specifying a list of values for each hyperparameter that you want to optimize and then training a model for each combination for these values. For example, if you want to optimize two hyperparameters, alpha and beta, with grid search, you would specify a list of values for alpha and a separate list of values for the beta. The grid search algorithm would then train a model using every combination of these values and evaluate the performance of each model. The optimal values for the hyperparameters are then chosen based on the performance of the models. Additionally, Additionally, it is recommended to use cross-validation when performing hyperparameters optimization with either grid search or randomized search. Cross-validation is a technique that involves splitting the training data into multiple sets and multiple training the model multiple times, each time using a different subset of the data as the validation set. This can provide a more accurate estimate of the model's performance and help to avoid overfitting. Here is an example of how to implement grid search in scikit-learn. So this is a sample program for the sim. So in this example, we can define the hyperparameter and their possible values in the parameter as a parameter. And that specifies the possible values for the hyperparameter alpha and beta. We then use the grid search CV class from the scalar model selection module to perform the grid search using these values. The fit method is used to train the model with the different combinations of the hyperparameter, and the best params attribute is used to access the optimal values for the hyperparameters. One disadvantage of the grid search is that it can be computationally expensive, and especially when optimizing many hyperparameters or when the list of the possible values for each hyperparameters is large. This is because grid search trains a separate model for every combination of hyperparameter values, which can quickly become infeasible as the number of combinations grows. Randomized search for hyperparameter estimator. The randomized search is another method for hyperparameter optimization that can be more efficient than grid search in some cases. With randomized search, instead of specifying a list of values for each hyperparameter, you specify a distribution for each hyperparameter. The randomized search algorithm will then sample values for each hyperparameters from its corresponding distribution and train a model using the sample values. This process is repeated a specified number of times, and the optimal values for the hyperparameters are chosen based on the performance of the models. Here is an example of the how to implement randomized search in scikit-learn, and this is the sample code. In this example, we define the dictionary called parameter distribution and specifies the distribution for the hyperparameter alpha and beta. We use the uniform distribution from the by stats module, which specifies the range of the values for each hyperparameters. We then use the randomized search CV class from the scalar model, the selection model to perform a randomized search using the distribution. The fit method is used to train model with the different combinations of hyperparameters, and the best params attribute to is used to access the optimal values for the hyperparameters. One advantage of randomized search is that it can be more Efficient and grid search in some cases, since it does not train a separate model for every combination of hyperparameter values. Instead, it trains a specific number of models using random samples from the hyperparameter distributions. This can be more efficient when optimizing many hyperparameters or when the distribution for the hyperparameters have a large range of values. It is important to note that both grid search and random search are only effective if the hyperparameter space is properly defined. In the other words, it is crucial to specify a reasonable range of values for the hyperparameter that you want to optimize. If the range of the values is too small, the optimal values may not be found, while if the range of the values is too large, the search process may be inefficient, takes a long time to complete. Comparing grid search and randomized search, again, in this example, we'll be comparing both the randomized search and the grid search using the toy data. So randomized search CV works by sampling random combination of hyperparameters from the search space and evaluating them using cross-validation. It can use sampling and evaluating until it has a tried the specified number of iterations. This means that it does not explore entire space, but rather a randomly selected subset of it. This can be more efficient than the grid search CV, which explores the entire search space, but it may also be less likely to be true optimal set of the hyperparameters. So why randomized search CV is better than grid search CV? One advantage of the randomized search CV over grid search CV is the randomized search CV can be more efficient if the search space is large, since it only samples a subset of the possible combination rather than evaluating them all. This can be especially useful if the model is computationally expensive to fit, or if the hyperparameters have continuous values rather than discrete ones. In these cases, it may not be feasible to explore the entire search space using grid search CV. Another advantage of the randomized search CV is that it can be more robust to the risk of the overfitting, since it does not exhaustively search the entire search space. If the hyperparameter search space is very large and the model is relatively simple, it is possible that a grid search CV and could overfit to the training model training data by finding a set of hyperparameters then works well on the training set, but not as well on unseen data. Randomized search CV can help mitigate the risk by sampling randomly from the search space rather than the evaluating every combination. It is worth noting that both randomized search CV and grid search CV can be computationally expensive, especially if the model is complex and the search space is large. In these cases, it may be necessary to use those techniques such as parallelization or early stopping to speed up the search process. So, in conclusion, what we can say is grid search and randomized search are two commonly used methods for hyperparameter optimization in machine learning. Both methods have their strengths and weaknesses, and which one is more suitable for the given problem will depend on the specific circumstances. It is important to properly define hyperparameter space and to use the cross validation when performing hyperparameter optimization to obtain the best results. Thank you.